Heat sealing is a very interesting topic, and especially so when you start to realize how often you run into it in everyday life. Consumer goods are heat sealed into bags for sale at grocery stores. Heat seals create inflatable air cushions to protect product through parcel deliveries. Even some clothing incorporates heat seals to offer waterproofing. These are some examples that everyday people come into contact with regularly. There are also a lot of high-value applications for heat sealing. Some of this is in the aerospace, electronics, or the life science industries. Our company, PacWorld USA, fits a great niche within these high-value industries, especially the life sciences such as medical devices, pharmaceuticals, or biotech. Heat sealing, developed as plastics were becoming more widely used. The first technology to market was constant heat systems, which involves heating a larger mass block that contacts the film to transfer heat and melt the plastic. Constant heat works well for films which are engineered with good hot tack qualities. Impulse heat sealing came after to solve the problem of sealing films which do not have great hot tack qualities, such as polyethylene. Impulse heat sealing involves energizing a low-mass heat sealing element instead of a large block of material. The advantage is the element quickly cools down below the set point when no longer energized, offering a cooling cycle within the heat sealing process so molten film can solidify and create a strong, hermetic heat seal with good cosmetic properties. Now, with this advantage, impulse heat sealing machines were able to seal all of the films constant heat devices can, and more. The trouble with early impulse machines was the lack of temperature control. It is easy enough to create a machine with controlled pressure and time parameters, but the first impulse machines varied temperature with a potentiometer if they had any temperature controls at all. Many low-cost impulse heat sealing machines still use this method today. A potentiometer is a dial that dictates power to the heating elements. The dial could be arbitrarily labeled from 1 to 10, and one of those numerical settings might produce desirable heat seals for an application. The first series of heat cycles may work well, but the machine starts to retain heat as it cycles over time because the same amount of power is applied for each cycle, resulting in over-melted heat seals. The typical solution in this example would be to manually dial back the power via your potentiometer. This relies on operator interaction, which slows the process down and introduces error. The next iteration of control is to incorporate a thermocouple feedback loop. A thermocouple is a temperature sensor which is placed directly on the heat seal band to provide feedback to the machine, allowing it to automatically vary power applied to the heat seal band. This was a tremendous gain at the time, but thermocouple controls have downfalls as well. Thermocouples take longer to read the full temperature output than typical seal cycle times. This inherent latency creates an accuracy issue. These sensors also degrade over time, becoming a consumable. Placement of the thermocouple is critical for the best temperature accuracy, and they can inadvertently move when using the machine, potentially causing the temperature to run far too hot. TOS technology came about as the highest evolution in impulse heat sealing controls and accomplishes this by using the heat seal band as a resistance temperature detector, also known as an RTD, that instantaneously reads the resistance of the heat seal band, which is equated to temperature and is able to do this at 50 to 60 times per second. Let me start by a quick overview of the system and how it generally works. TOS technology utilizes its PIREG brand heat seal controllers within a closed-loop system consisting of the PIREG controller, properly sized power transformer, current transformer, and seal bars or heat seal platen configuration. The seal bars or heat seal platen is the specific tooling used to create a heat seal and consists of structural components to give the tooling its shape, the heating elements, and some other consumable layers which provide compliance and film release properties for the heat sealing cycle. When an application is properly configured with the TOS system as used on PacWorld machines, the result is fast heat up times, accurate temperature monitoring, and a very high degree of repeatability. The main concept making all of this possible is Ohm's law, which states resistance is equal to voltage divided by current. The PIREG controller uses Ohm's law to monitor and control the current and voltage to obtain a specific resistance. Because a known alloy, which we call alloy 20, is used to manufacture the heat seal bands and has a known resistance curve, a specific resistance can be calibrated to a specific temperature output and then accurately and repeatably produce that same temperature output. All that said about the technical pieces, the TOS PIREG system used within PacWorld machines provides a validatable heat sealing system, meaning you can verify the performance and have confidence the system performs the same over time. This is essential in life science industries where the FDA or other notified bodies require a validated process. The system fits well into other high-value industries such as aerospace, where failures are just not acceptable. Better temperature management also benefits high-volume applications such as consumer goods and food, where packaging scrap rates and downtime can be avoided. The future is always fun for me to contemplate. Although the core concepts of our technology have remained the same, there have been many advancements over the last 35 plus years we have been working on heat sealing applications. Some are in the form of honing calibration methods. For example, PIREG controllers now have the capability to incorporate a single or multi-point calibration method. A lot of our innovation is fed through customer feedback. For instance, we had some customers needing to change tooling configurations in automated equipment. So a feature called measurement pause was created, which allowed the controller to avoid an alarm state when the electrical signals dropped intermittently when the tooling was switched. We also incorporated multiple stored calibrations to accommodate different tooling sets. Each unique project or challenge helps us think a bit differently. It feeds our curiosity, it keeps us striving for continuous improvement.